All right, so guys, on this power and work assignment here, okay, we just want to recap a couple different things. Work is equal to force times distance times cosine of theta. Now, if there's no angle given in the problem, that means that theta is equal to 0, and when you take the cosine of 0, it's 1, so pretty much it disappears. So if they don't give you an angle, you don't need to do cosine. So work, therefore, would just be force times distance. Now, the unit for work is the joule. The unit for force is the newton. The unit for your distance or displacement is the meter. And if they give you mass in a problem and ask you for the work done, it's probably going to be that you're lifting an object, in which case the force of gravity, all right, on the object, or the weight of the object, mass times gravity, will be your force. Then to find power, capital P, right, is equal to work divided by time. Now the unit for power is the watt, and sometimes here it is labeled as a capital W. Like here, they wanted to know work done by a 600 watt motor in 30 seconds. So this, since it's following that, that's referring to the unit. So you're given P and you're given T. So to find W, it's power times time. All right, now there's a problem over here. Okay, another way, if work is equal to force times distance, and you do replace W with F times D, power can also equal force times distance divided by time. I think there's 2 or 3 problems like that use this. Okay, here, how much power does it take for you to lift a 40 kilogram object 15 meters high in 20 seconds, right? So you were like, oh, I have something, something, and something. Power. All right, so I look to power. Power is W divided by T. I don't have anything in joules, so I can't use P is equal to W divided by T. What do I have? I have meters, okay, which is the unit for distance. I have time, okay, that's good. So I have D and T. I don't have F. So I wrote here, right, if you're given mass times gravity would be your force. So you got to do that first. That will be the F in this equation. In 7, you have 2 things here. They're asking which one does more work. Multiply this one together, multiply this one together. Circle the one that produces the most amount. For 10, you have to use potential energy is equal to mass times gravity times height. Here's your mass. We're just use 10 for gravity and then times it by the height. So for number 11, he drops the backpack just before it hits the ground. So I tried, mentioning this earlier. Okay, if this is a ledge, all right, a little cliff, and you have a ball here, and then if it drops it to go to here, and then we'll just put it right down here. All right, at the top, if the potential energy equals, let's just say, 100 joules, it's not moving, so the kinetic energy will have to equal 0 joules. Now, the mechanical energy is the sum of those two, so you add these two together. So 100 plus 0 gives us, right, a mechanical energy of 100 joules. So the ball has to be a total of 100 joules at any single one of the points as it's falling. So if I just said to you right here that PE, all right, because as it loses height, it loses potential energy. So let's just say PE was 70. That is an awful 7. If PE was 70 joules, what would the kinetic energy have to be? It would have to be, what number? 30. 30, good, because no matter what, at any single point, it has to be this mechanical energy total. So this would have to be 30. Now, when we show the picture like this right at the bottom, usually it's going to be saying like right as the object hits the ground. So when we're talking about that, we're basically saying that the height is 0. So if height is 0, your potential energy is going to be 0. And we would just say, all right, because that is the maximum speed it's going to finish with and hit, all right as it's hitting the ground. So in this case, the kinetic energy would be what? Or it has to be what? 100. So for that same reasoning, okay, your answer here is going to be the same as it is in number 10. So number 10, you find potential energy because that's what the backpack is at the top. And as it drops, it's losing potential, but it gains kinetic. And then right as it hits the ground, all the energy is kinetic. So if you knew what the mass or the total energy was, potential energy at the top, where kinetic is 0, then down here where potential energy is 0, kinetic would have to be that same number. So it should be a pretty large number. And then in number 12, you would use this equation. You're rearranging the kinetic energy equation. Mass is equal to 2 times the kinetic energy divided by v squared. And for 13, I just rearranged the equation for you. T is equal to force times distance divided by P. You do not have to do 14. You do not have to do 14. Okay. So, pretty much, guys, if we had some notes here for energy, kinetic energy is going to equal the work on an object, work done on an object. And it basically takes kinetic energy is equal to work. Well, if work is force times distance. And it basically shows you, breaks it down. All right, basically a simple how the heck we came up with the equation is 1/2 mv squared. You don't need to know how to do all that. It's just being shown. But you do need to know this equation. Kinetic energy is 1/2 mv squared. Okay, doubling the velocity quadruples the kinetic energy. There's a couple example problems for you to look at here. Now, potential energy equation. I think it got a little bit cut off on your notes, so if you want to write that, it's essentially the same premise, same idea. Potential energy is equal to work done on an object, all right, or the potential energy an object has could be the work done by the object or on the object. So potential energy, force times distance, because that's what work is. Okay, we simplify out. Force here would be the force of gravity, which is m times g, and if d is height, we rearrange it to mass times gravity times height. So potential energy is mgh. Mass times gravity is weight, which is our F sub g. We can throw this into the triangle over here. So this triangle works just like our others. If I asked you to solve for PE, if I cover up PE equals mass. If they're right next to each other, you multiply. So mass times gravity times height, which is our equation over here. If I asked you guys to solve for height, H equals PE, right? If I asked you to solve for H, cover it up. You have PE, and since it's over those two, it's divide, okay? Mass times gravity. And if I asked you to solve for M, it would be PE divided by gravity times height. All right, again, there are a couple problems, sample problems on here. They ask you, okay, how much potential energy or gravitational potential energy does this book have? Well, you're given a mass, 2 kilograms. They tell you in this little diagram I tried drawing that if we place a book that is 1.8 meters above the floor, how much potential energy does it have? Well, the mass of the object was 2. Okay, so PE is mgh. We're using 10 for gravity, so 2 times 10. And if it was 1.8 meters above the ground, okay, that would be your h. Multiply everything out, you would have 36 joules worth of potential energy. But then they ask, okay, well, how would it be? How much potential energy would it have relative to a table that's 0.6 meters above the floor? So that one's a little bit trickier because sometimes people just use 0.6 as the height. No, they're talking about the book, all right? They're talking about the book relative to the floor. I'm sorry, relative to the table. So if the whole thing is 1.8 and the table is only 0.6 meters above the ground, if we were to drop from the top shelf to the table, it would have only fallen this distance of 1.2 meters. So in that case, that would have been your height. And you would have gotten 24 joules. And it should make sense, right? So like if this is someone's head and you had a ball and you're going to drop the ball, from this height versus this height. All right, this one is definitely going to allow there to be more potential energy to be converted to kinetic. It's going to hurt more, less height, less potential as it drops. Okay, it's not going to have nearly as much speed. Then we talked briefly about the law of conservation of energy. So energy can be transformed from potential to kinetic and vice versa. So we looked at that in the roller coaster thing from yesterday. Law of conservation, energy can change form, but it cannot be created nor destroyed. And then you needed to also know that for our closed isolated system, the total energy, right, our total mechanical energy, is the addition of potential and kinetic energy. It's the sum of those two. Now, once you find the mechanical energy at any point in this system, it's going to remain constant. Okay, then we looked at a conservation of energy equation here. We spoke about it briefly. You can rearrange the kinetic energy equation to solve for V, which you will need to do on that assignment. And then also for this, I don't know if it will be needed, but it would be 2ke, where are you at? 2ke over V squared if you needed to find mass. So you guys can write that in there. And we're not going to worry about the collisions right now. We're not going to talk about those. So the worksheet that you're getting now, So guys, in this one, each one of these statements, we have to identify what they're talking about, whether they're talking about kinetic energy, potential energy, or both. Remember, kinetic energy has to deal with the fact that an object is moving. Potential energy has to deal with the fact, or what we're talking about, gravitational potential energy, has to deal with the fact that the object is a certain distance above another object. Okay? So if an object is at rest, what does it definitely not have? Kinetic. Good, Ke. Depends on the mass and height. Which one would that be? Well, they both have mass, but which one has height in their equation? Pe. Good. The energy, right? So if these are the equations, and potential energy is mgh. 3, the energy an object possesses due to its motion. What? Kinetic. The amount is expressed using the unit joule. Both, yes, both. All right, all energy we're using, is going to be use joule as the unit. Energy stored in an object due to its position or height. Pe, right? It's got height in it. There's our H, ba-bam-bam. Number 6, this depends on the arbitrarily assigned zero level. So basically, like in the problem that I showed you guys before of the book, relative to the ground or relative to the table. Potential energy, yes. Depends on the object's mass and speed. Ke, bam, bam. And number 8, if an object is at rest on the ground, zero height, it definitely does not possess this form of energy. Why both?
Because if it's on the ground, the height is 0.
Zero height and?
No energy. It's at rest.
Very good. So it's at rest and zero height. So it does not possess either. So that one's a both. All right, really quickly before the rest of you guys should be able to do with the notes and everything, these two. Kinetic energy is 1/2 mv squared. Since the 1/2 is constant, if we replace this as a 1's equation, it'd be 1 times 1 squared. All right, where this one is m, this one is v. They said, okay, if the speed is doubled, so they did not change m, so we leave it a 1. They said that speed is doubled, so v would become a 2. And what is 1 times 2 squared? 4. So it would be 4 times as much. Now they gave us a value of 0.40. So you would do 4 times 0.40, which is 1.6 joules. So letter D. And then the next problem is MGH, mass times gravity times height. They didn't tell us anything else changed except for the height. The height doubles, so mass and gravity stay chilling. Height becomes a 2. What's 1 times 1 times 2? All right, so again, this would be 2 times as much. But in this one, they're telling us the original energy is 80 joules. So you would do 2 times 0.8, which is 1.6 joules. So this one is letter C. Okay, the rest you guys should be able to do. Again, number 8, you're going to use. Number 8, you're going to use this equation here. So everyone rewrite this equation in on number 8. And then the very, very last thing I'll show you, number 11 is super easy. Because they want the mechanical energy at any one of those points, mechanical energy is kinetic and potential at any single spot. So in this case, you're going to just add them together. That's it. Now, if this was a perfect system with no friction, when you add these two to get 10,000, you should also be 10,000 here. But when you add these two up, it's 9,000. So how much energy was lost? 1,000, right? Because 10 minus 9, there'd be 1,000 joules worth of energy was lost due to the friction between the board and the snow and whatnot. Okay, so you guys can definitely finish those off. It'd be super easy. You guys did a great job today. Mr. Lombardo, you did a great job today. Thank you, Mr. Lombardo.